Okay, today we're picking up with limits at infinity of rational functions. So the first one that I want to look at is whenever the numerator and the denominator have the same degree. Remember, the degree is just the highest exponent. In this case, it has a degree of 2 in both the numerator and the denominator. So whenever this happens, what we actually want to do is we want to take the top and bottom and divide each term by the highest degree. And I'm going to show you how that's going to work and why it helps us. So if I take the first term, can't forget to write limit as x approaches infinity. If I take the first term and I divide it by x squared, then that just leaves me with 5. Then plus 8, and 8x over x squared, if you'll remember, that's the same as 8x over x times x. So one of your x's will cancel out. You're left with 8 over x. So it's going to be 5 plus 8 over x, and then minus 3 over x squared. Let's divide the denominator by the same thing. 3x squared divided by x squareds. Those x squareds cancel. And I'm left with just 3. And then 2 divided by x squared is just 2 divided by x squared. Now I can take the limit of each part of this. So the limit of 5 is just 5. The limit is x approaches infinity of 8 over x. If you remember from yesterday, we learned that any number divided, if it's just a number, divided by x or the variable is going to have a limit as x approaches infinity of 0. Because as x keeps getting bigger and bigger, my decimal keeps getting smaller and smaller. So if I have 8 divided by 10, that's 0.8. But as I keep going further and further out towards infinity, 8 divided by 10,000 is going to be 0.00008. 8 divided by 100,000 is going to be even smaller. So it's going to get closer and closer to 0, and that's what our limit would be as x approaches infinity. Same thing for 3 over x squared. If I do 3 over x squared, this one's going to be even smaller. So using the squeeze theorem that we learned last section, and the fact that we know that anything over x converges to 0, so does this. So that would be minus 0 over, and now I just have 3, and then 2 over x squared converges to 0, so that would be plus 0. 5 plus 0 minus 0, it's just 5 over 3. That's my limit if they have the same degree for the numerator and operator. I said numerator and operator, I meant denominator. So let's move forward now and look at when it's the degree of the numerator is less than the degree of the denominator. I'm really going to go through the same process here. So if I go through the same process, I'm going to find my highest degree. That would be this x to the third. And I'm going to divide every term in the problem by x to the third. So this would be the limit as x approaches negative infinity. And then 11x over x to the third is just going to give me 11 over x squared. 2 over x to the third is just that. Over 2x to the third over x to the third is just 2. And then minus 1 over x to the third. If I'm looking at the limit as x approaches negative infinity, then this is going to be increasingly closer to 0. So the top part is 0. So is this one. That would be 0 plus 0. On the bottom, I would have 2 minus 0. Give me 0 over 2, so just 0. Now, we can take what we just learned about when the numerator is less than the numerator has a degree that's less than the degree of the denominator, and we can apply that to all future cases. So now it doesn't really matter what I'm looking at. If I start with a problem that is the limit is x approaches negative infinity of x to the 7th plus x to the 6th plus 4x to the 3rd plus 75x to the 9th. I don't want to go higher than 7, but because I'm listing it in order, plus x squared plus 21x all over x, we'll go to the 9th, plus 7,400 x squared. I said 7,400, that's 700,400 plus x. All I need to know is that this x to the 9th is going to make every one of these in the top converge to 0. So they're all, the limit of each one of these is going to be 0. Because my denominator is higher, so this would automatically have a limit of 0 as x approaches either infinity or negative infinity. So it's important to take the lesson that we just learned and apply it to future examples. You can make it real simple as soon as you know that as soon as that I see that my degree in the top is smaller than my degree in the bottom, the limit as it approaches infinity, and that's the only time it works, is negative infinity or positive infinity, is going to make it go to 0. So make sure you're applying that lesson to all future lessons. That gives us a horizontal asymptote. So a horizontal asymptote, a line y equals b, is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity of the function is equal to b, or the limit as x approaches negative infinity of the function is equal to b. So if I have a horizontal asymptote, it tells me that the limit of the function has to be equal to whatever my horizontal asymptote is. All right, so we start with the curve f of x equals 5x squared plus 8x minus 3. It has the line y equals 5/3 as a horizontal asymptote on both the right and left because the limit as x approaches infinity of f of x equals 5/3, and the limit as x approaches negative infinity of f of x equals 5/3. If I needed to graph that in Desmos to see that that's true, and so now going to Desmos, I type in my equation, 5x squared plus 8x minus 3 divided by, I should put this in parentheses, it'll make it easier to do my divided by, and then 3x squared plus 2 Okay, so if I'm looking at this now, I have a horizontal asymptote that I can't see yet. But as you look at this, you zoom out, you can see that my line kind of just flattens out. It doesn't go any lower, and that's because I have a horizontal asymptote at 5/3. So So if I just do y equals 5 over 3, you'll notice that I have this horizontal asymptote that the red never touches the blue. It'll look like it's getting close, especially as I zoom out, but it never actually touches. I can zoom in on any spot, and once I get in far enough, it's never actually going to touch the blue on either side. I could also just grab a dot on the red, not where one of the dots is, but just grab a random spot and drag it all out, and it's never going to go less than 5/3. So that's a horizontal asymptote. And by finding those limits at both infinity and negative infinity, we can prove that that horizontal asymptote exists. Okay, a curve may cross its horizontal asymptote. So just because it crosses, though, does not mean that the horizontal asymptote does not exist. If we look at this function, y equals 2 plus the sine of x over x, whenever I look at this, I can see that it's going to level out at 2. And plus, we know sine theta over theta is equal to 0. Is our limit. So then this would just be 2 plus 0 if I was taking the limit as x approaches infinity. And so we have our squeeze theorem, or our sandwich theorem, that said that if I knew like the limit of something went to 0 and I had one that was either smaller than that or bigger than that, but between it and 0, that it would sandwich it down and push it down so that it actually went to 0, so that I could use an easier function to find it out. So the sandwich theorem still exists whenever we go to positive and negative infinity. So it does not go away. And again, if I just took the limit as x approaches infinity here, I know that this is 0. 2 plus 0 is just 2. So that would give me my limit as x approaches infinity of this function equals 2. Same thing with negative infinity. If we looked at this dragged out more, like if I had a bigger version of this function, 2 plus sine x over x. So this is the zoomed in version that we're seeing on our chart, or on that graph I had up there. So that's the zoomed in version. But you see my waves really start to flatten out. And again, I can see little ripples here, but eventually it just flattens out to a straight line. So that it is going above and below 2, but it's happening at such a small amount that it's actually converging to that point. See what I mean? So that horizontal asymptote still exists. Lastly is oblique asymptotes. So we talked about when the degree of the numerator is the same and when the degree of the numerator is smaller. But if the degree of the numerator of a rational function is 1 greater than the degree of the denominator, the graph has an oblique asymptote. Oblique just meaning slanted. We find an equation for the asymptote by dividing the numerator by denominator to express f simply as a linear function. So it's just a linear function plus a remainder that goes to 0 as x approaches positive and negative infinity. So here's an example of that. I have 2x squared minus 3 over 7x plus 4. So if I start by doing what we had been doing with these, move this out of the way, and divide everything by the highest degree, Or if we just do long division, that's actually the best way. So if I do long division, I have 2x squared minus 3, and then 7x plus 4. So how would I get to 2x squared if I have 7x? I would have to multiply by the fraction 2/7 x. Because 2/7 x, 7 times 2 is 14. 14 divided by 7 is 2. So then this now makes this minus 2x squared. X times x, it's the x squared. Now I have to multiply the 4 times 2/7 x. So that would give me minus 8/7 x. Those ones cancel out. Here, if I have negative 3 minus 8/7 x, that doesn't work. I'm going to show you why. Rookie mistake. This was x squared, and then I didn't have anything at all. I need to have a 0 as a placeholder in here, 0x, and then minus my 3. You have to drop by one term each time. So it would be 2, x to the 1 first, or to the 1, and then x to the 0, because there's no x at all. That's better. So now I have negative 8/7 x. So what would I multiply 7x by to get negative 8/7 x? Well, I'd have to multiply that by negative 8 over 49. 7 over 49 is going to reduce to just 1 over 7, and then times 8 gives me 8 over 7. Flip my sign, and I bring down my 3. Flip my sign, this becomes plus 8/7 x, and then I multiply this out, 4 times negative 8 over 49. That's going to give me negative 32 over 49, which is awful. My 8/7 x's cancel out. Now I'd have to find what a common denominator of 49. So 3 times 49 for my numerator would be 147. This would be negative 147 over 49. That's what the 3 turns into, getting a common denominator. When I did negative 8 times 4, that gave me negative 32 over 49. And then you have to flip the sign to make that a plus. So plus 32 over 49. This gives me negative 115 over 49 times whatever I divided by, which is 7x plus 4. The front portion of this, all of this, is my equation for my oblique asymptote. This part here is going to converge to 0. So if I take the limit as x approaches infinity of this, this is going to keep getting bigger and bigger in the denominator, which makes this whole thing go to 0, and I don't have to worry about that anymore. Okay. On Monday, we're going to do some more examples of this and go over homework. Then on Tuesday, we will kind of do a review of 2.1 through 2.4 and answer any questions you have. On Wednesday, you will have a quiz on 2.1 through 2.4.